Welcome back to Math 104. In a certain state, 50% of voters are Democrats, 40% are Republicans, and 10% are Independents. Based on polling data, 40% of Democrats support a certain referendum on the upcoming ballot, 60% of Republicans support the referendum, and 70% of Independents support it. Before we do anything, let's stop and think what information is conditional and what information is unconditional. The information here is conditional because each given percentage tells us about only a certain subset of the population. 40% of Democrats, not 40% of everyone, but 40% of Democrats. That is conditional information. Up here we have unconditional information. Each percentage is a percentage of the entire population. In order to understand an ideal dataset consisting of 1,000 voters, we could first draw a tree diagram with its initial branching based on unconditional information into Democrat, Republican, or Independent, and from there, the second branching based on conditional information into supports the referendum or doesn't, supports or doesn't, supports or doesn't. We could do that, but let's use this example to see how it would work to move directly to the ideal dataset. We are told that 50% of voters are Democrats. Out of 1,000 voters total, that means 500 of them in an ideal dataset are Democrats. Similarly, 40% of all the voters are Republicans, and 10% of all the voters in this state are Independents. So we can fill in this column of totals, and working from there, we can now apply the conditional information. 40% of Democrats, 40% of these 500 voters support the referendum. 40% of 500 equals 200. That means that the other 300 Democrats do not support the referendum. Among Republicans, 60% of 400 people, that's 240 voters, support the referendum. The other 160 Republicans do not. Finally, 70% of these 100 Independents, that's 70 voters, support the referendum. The other 30 Independents do not. That wasn't so bad. We have actually not worked with any decimals at all in order to produce this table so far. We keep going to find the column totals. There are a total of 510 voters out of 1,000 who support the referendum and 490 who don't support it. So the voting public is very closely divided on this referendum, whatever it's about. Now let's compute some probabilities, or equivalently, percentages. If the polling data can be believed, then what percentage of voters voted yes? And is it over 50%? The total probability of the event S equals 510. This 510 over 1,000. This is an unconditional probability. We're asked what percentage of voters, of all the voters, voted yes. And this is indeed over 50%. It equals 0.51. That means that if there was a 50% threshold for passing the referendum, then it did indeed pass. Before we get too immersed in this approach of using ideal datasets and frequency tables, let's remember what this question has to do with conditional probability. Probability of S, that is the total probability of S, the total probability that a randomly selected voter supports the referendum, equals the probability that a voter is a Democrat and supported the referendum, plus the probability that the voter is a Republican and supported the referendum, plus the probability that the voter is an Independent and supported the referendum. The event S is the union of these three smaller events. If we think back to tree diagrams, we can recall how each of these probabilities was computed. The probability of D intersect S was computed as the probability of D times the probability of S given D. We were told 50% of all the voters are Democrats, and 40% of Democrats support the referendum. This 0.5 times 0.4 equals 0.2, and therefore 20% of all voters are Democrats supporting the referendum. Built into that computation was this conditional probability right here. Similarly for Republicans, the probability of R intersect S equals the 0.4 probability of R times the 0.6 probability of S given R. And that equals 0.24. 24% of all voters are Republicans supporting the referendum. This 20% shows up as 200 Democrats out of 1,000. This 24% shows up as 240 Republicans out of 1,000. And the same story holds for the Independents in support of the referendum. 10% of all the voters are independents, 70% of the independents support the referendum. That's a conditional probability right here, equal to 0.7. That gives us 0.1 times 0.7 equals 0.07. That's 7% of all voters are independents who support the referendum. That 7% of 1,000 voters equals this 70 right here. The quick approach we used here to filling out this table should not lead us to forget the thought process behind the tree and the role of conditional probabilities in it. Another question. A voter walking out of the polling booth is selected at random and says that she voted for the referendum. What is the probability that she is a Republican? Let's stop and think. Conditional or unconditional? This is conditional on the knowledge that she voted for the referendum. The probability we need to find here equals the probability of R given S. Knowing that she supports the referendum, what is the probability that she is a Republican? Since we know that she is one of these 510 voters who voted yes, our probability is a fraction out of 510, and there are 240 ways that she could be a Republican. Therefore, 240 over 510 equals the probability here. This is approximately 0.4706. If we had no idea how she was going to vote on the referendum and wondered how likely is it that she's a Republican, the chance would be 400 out of 1,000. But knowing that she voted yes on the referendum causes us to revise our assessment of this likelihood upwards to 0.4706. We are more likely to think that she is a Republican after finding out that she voted yes than we were before we knew anything about how she voted. Before going on to the next video, answer the following questions. A voter walking out of the polling booth is selected at random and says that he voted against the referendum. What is the probability that he is an independent?